Good afternoon, everyone. My name is Mary Beth McCucci, and I'm the Director of Learning at NAFA. Welcome to our webinar today on signaling prioritization in the transit and emergency vehicles. Before I turn things over to our moderator and speakers, just a few quick housekeeping items to note. This session is being recorded and will be posted on the North Carolina Clean Energy site. More details for that will be sent out to you. And we do have you all muted on the call just because we want to keep the background noise at a minimum. However, we do encourage you to ask questions in the chat or the Q&A section, and you can find that at the bottom of your Zoom taskbar. If you do experience any technical issues, please feel free to reach out to me via chat. I'm certainly here to help you. And now it's my pleasure to introduce our moderator today, Alric Lunsford. Please go ahead and begin.
Good afternoon, everyone. My name is Alric Lunsford. I'm with the North Carolina Clean Energy Technology Center, Clean Transportation Specialist, and wanted to welcome you all to today's webinar that we're going to be discussing. Before we get started with that, wanted to provide a little bit of a background about the North Carolina Clean Energy Technology Center. And the center provides services to public entities, governments, businesses, utilities, and citizens relating to the development and adoption of clean energy technologies that includes the transportation sector. And through the program and activities, we envision and seek to promote the development and the use of clean energy in ways that stimulate a sustainable energy economy. We're proud to partner with NAFA, the world's largest membership organization for individuals who manage vehicular fleets as well as mobility responsibilities. And with this webinar, we aim to look at some of the frequent occurrences in urban environments, whether it be through timely response for emergency services, as well as reliable transit schedules that are critical. And so this webinar will delve into the innovative signal prioritization techniques that can significantly improve traffic flow and reduce response times for emergency vehicles, as well as enhance the reliability of the public transportation systems. And we would definitely like to thank our sponsors for the webinar. Without them, none of this would be present, or none of this would be able to take place. Our sponsors, and let me our sponsors are the United Soybean Board, as well as Leak Services, eBoost, and Geotab. And said these sponsors are what help us keep us afloat with our the different types of services that we provide. And so going into some of the upcoming events that we have. So we have a couple of webinars that are coming up. One on November the 20th, focusing on key performance indicators for telematics and dashboards. And then one on December the 4th that is going to discuss off-road electric equipment. And NAFA also has some upcoming events. Feel free to register for any of NAFA's events by going to nafa.org, as well as / sustainable fleet technology. Next slide is NAFA's biggest conference, the INE Institute Expo, that will be in Long Beach next April the 28th through the 30th. So we definitely encourage you all to scan the QR code, go ahead and register as registration is currently open for that conference. And the North Carolina Clean Energy Technology Center Clean Transportation Team also facilitates a conference called the Sustainable Fleet Technology Conference in April, conference and expo that will be occurring at the Bend Convention Center in Winston-Salem, North Carolina, next August, August the 25th through the 27th, 2025. And if you click on the link below, you can also be able to go onto that website as registration is open to go ahead and join us in Winston-Salem for that conference. So next we have our speakers. We have Brad Verrier from Myovision, Seth Searle from Kimberly Horn, Peter Kuntz from the city of Portland, and Owen Kehoe, King County, Washington. I'm going to stop sharing my screen for a second so I can be able to just briefly give you all a little bit of background about the presenters that we have. So very thankful to these four gentlemen for speaking on this topic today. But and they're all very dedicated and extremely thankful to Brad. Today's his birthday. And so you all make sure that you definitely um want to welcome Brad with some good well wishes and don't want to hold the webinar too long. And with that, want to get into a little bit of their background. So with Brad Verrier, he has been part of the MyoVision team, and as part of the team, he builds out the holistic approach to intersection technologies in the United States and across the world for their ecosystem. And so with that, Brad, I am going to go ahead and share my screen again and hand it off to you for your presentation. Just wait for a second to let PowerPoint slides catch back up to us.
Sure, I can just start chatting then. Yeah, my name is Bradley Verrier. I'm the solutions engineer at MyoVision. So I cover all the different technologies that we provide. So I'm going to be going over how to facilitate and track continuous movement as a means of reducing congestion. So to start off, I wanted to talk a little bit about how congestion is able to impact um, the way that we operate at the intersection. You can go to the next slide. So the impact of congestion on emissions is pretty substantial, right? It's very much a one-to-one relationship. And there's certain ways that the government can tackle it from the vehicle standpoint, where we can reduce the amount of emissions that vehicles produce. A lot of different vehicle agencies have managed to lower emissions while idling by turning off the engine when we stop. But obviously, the best way to make sure that we are lowering emissions is to reduce congestion. If vehicles are moving continuously from point A to point B, there's going to be a lot less emissions being pumped into the air because they're not forced to idle to keep burning gas when they're not moving anywhere. So obviously, the best way to reduce emissions is to reduce the number of vehicles on the road. But given our current infrastructure, that's obviously very difficult. So the next best step is to try to make changes at the intersection level to optimize how traffic is flowing through your grid. So what we try to do is look at a bunch of different methods for understanding how to continuously move vehicles, and then a separate set of functionalities that allow you to track the progress as you do so. I'm going to be covering a couple different technologies in this presentation. I have done my best to make this not a sales pitch. Most of these technologies are different providers who provide the systems through slightly different means. And we're going to look a little bit on the vehicle side in one of the later presentations. So for today, I really want to focus on just general practices that you can do to facilitate and track continuous movement. So to start off, we're going to be going to look at the facilitating the continuous movement. If we can go to the next slide. I'm just going to do this when I want to go to the next slide, Alric.
Okay, yeah, having a little bit of technical difficulties with slide advancement. Stop sharing my screen for a second.
I can always share my deck if you'd like. Here we go. So I've
Okay.
listed a couple different ways that you can facilitate continuous movement, and we're going to go look at each of those a little bit more in detail as we go through. So we're going to be looking at optimizing detection, looking at multimodal considerations, particularly for vulnerable road users, emergency vehicle preemption, transit and fleet priority, and adaptive control. So to start off, for the detection side of things, I wanted to talk about what the ideal detection is for congestion mitigation. So the camera that's being used here is a MyoVision camera. This is a GIF that is not loading particularly well on Alric's older version of PowerPoint. It's also a 4K video that we've throttled down to a lower resolution just for data storage reasons. But what I wanted to demonstrate is that you can use your detection for more than just vehicle detection. There are many systems in the market today that allow you to not only look at where your vehicles are stopped, but also where your vehicles are throughout the intersection. And if you go into your detection platform, not only looking at the bare bones of what you need to accomplish today, but looking at all the additional functionalities you may need to leverage going forward, it's important to understand a few different things to look out for. Obviously, you want to be able to do stop bar presence and pulse detection with flexible configuration. You want to make sure that the system allows you to detect things like pedestrians and bicycles, so you can optimize more safely and leverage specialized applications. And you need to be able to do vehicle classifications so that you can understand exactly how you're. If you have your detection configured, set up in a certain way that allows you to classify both vehicles and individuals, it allows you to do specialized applications, including pedestrian extension, where you can track if a pedestrian's in the crosswalk, place a detection call, and then hold either the green time or the all red to allow those pedestrians to clear safely. Now, that might not be something that you're looking at today, but making sure that you have the proper detection set up can actually really help that. When we are configuring pedestrian clearance times, we often have to assume a very high number. However, if you are actually tracking if pedestrians are in the crosswalk, you can set your clearance times for the average individual and extend that call if needed by understanding what's actually in the crosswalk. So leveraging a detection platform that gives you all the information about the intersection gives you a great start to understanding what functionalities you need to include to make sure that you're properly accounting for all of the different road demands. On our next slide, we're going to be talking about um, priority control. So priority control is a bit of a blanket term, and it's used for what's often called EVP and TSP, which is emergency vehicle preemption and fleet and transit signal priority. So there's a couple different types of priority calls that are going to be very dependent on who's using it. For example, if a public safety professional is using the intersection, say an ambulance, we're going to want to be giving it a green phase as quickly as is safe. So that's within regards to if there's a pedestrian currently in the crosswalk, making sure that we have our pedestrian clearance and our vehicle clearance times set up correctly. We're preempting in advance so that as soon as they get to the intersection, they can get through as soon as they can. Conversely, when we're working with things like transit, fleet, snowplows, and other systems, it's a little less important that they get the green light right away, and it's more about leveraging them alongside detection so that vehicles that have more importance, whether that is freight that needs to be very much on time or transit to make sure that our bus routes are working as smoothly as possible, We can essentially track those vehicles and figure out if a priority call should be made to either extend that green phase to allow them time to clear or end the previous phase early so that they can get a green light as soon as they can within the context of the overall traffic operation. Within these different agencies, we can also set relative priority so that if you want only certain intersections to respond to transit, but perhaps right outside of a fulfillment center or a major shipping district, both your freight and transit respond to the same priority calls, you're able to customize that to make sure that you're only placing the calls that you should within the bounds of your own agency as well as the traffic department. When we talk about priority control, we need to look at the three different models that we used. So on the next slide, we're going to be looking at the three different models that we've leveraged. The first is IR. Opticom was, we believe, the earliest in the space when it comes to preemption. And for almost 50 years, IR was the only way to go. The way that we did that was through IR emitters on the vehicles, which were connected into the IO wiring harness. And we were able to basically make a customized flashing signal which would be collected by the IR detectors at the intersection facing each approach that is using priority control. We communicate that down into the controller through a dedicated piece of hardware. We then moved on to radio, where we took essentially a very similar solution from the vehicle side, except instead of using an IR emitter, we're now using radio, much less line of sight based, and we only need one detector on the intersection side, so it's a lot easier to maintain. And then very similar on the intersection side, how that radio communicates into the traffic controller. So this did solve a lot of the issues with IR, but there was still a lot of room for growth. Most preemption systems today leverage a cloud model. The cloud model generally either uses direct CAD AVL data. We can leverage GTFS or different, freight data feeds, as well as modems in the vehicles, which are transmitting the current status of the vehicle as well as its exact location. And then from the intersection side, you can either leverage hardware to communicate to the controller, or many systems, including MyoVisions and others, are able to leverage a direct connection to the controller without any need for intersection components. So the cloud model really filled in a lot of the gaps for the older systems. It provides a lot more data because of how we're able to communicate in and out of the intersection, both vehicle to intersection, as well as, when you're trying to review the system, customize the system. It really simplified a lot of those processes. And I wanted to include a slide kind of showing how all of these different systems work in conjunction. So you can see a lot of different vehicles here that are equipped with TSP. Each of them has a different type of relative priority, either falling into the high priority for EVP or low priority for transit and freight. And we're able to accommodate these different signals based on a first in, first out system within to the relative priority that's been set at the vehicle and the threshold that's been set per intersection. So doing this, we're making sure that the right vehicles get calls, and we're able to expedite all of these different public services within the rules that have been set inside of the controller. Next, I want to talk just briefly about adaptive control. It's not the topic of today's discussion, but I wanted to give you guys a quick understanding of how adaptive control also allows you to account for the vehicles that are using your road. Adaptive systems function based around understanding the current input at the intersection and then accounting for what operations need to be made to expedite those vehicles. In MyoVision's case, we're leveraging the same hardware that the preemption system and the detection system would use, but there's lots of different ways to do adaptive control, whether that's through a hardware implementation or directly through a controller. And these allow you to accommodate not just public service vehicles, but also standard cars as well. One of the big advantages of adaptive control, if you set it up correctly, you can actually leverage things like transit signal priority inside of the context of adaptive control so that we're accounting for transit not in the vacuum of there's a bus coming, it needs a green light, But if I notice that there are 30 vehicles trying to head east and one bus trying to head north, I'm going to give the priority to those 30 vehicles because it allows us to weigh those buses inside of the context of overall traffic. All right, and now we're going to move on to the second half of the presentation around tracking continuous movement. So I wanted to cover a couple different things around how the intersection's operating and the effects that all of the things that we went over in the previous section have had on how the system is operating. So we're going to be covering signal uptime, intersection utilization, reducing collisions, transit and freight effectiveness and consequence, ATSPMs, and the value before and after analysis. So starting off with the signal uptime, this is really about tracking anything that could be going wrong across your network. Whether that is an intersection in flash, a lack of detection information coming up, power outages, detection failures, any issues with any cabinet level technologies, you're able to monitor those and get alerts for anything that's going wrong. If you're trying to remove congestion, a great way to do that is to make sure that all of your intersections are running. So to do that, there's a couple different things that you can do. You can review the signal telemetry, make sure that your signals are operating the correct way, as we can see on the left side there. And you can also track how detection and preemption calls are being handled by your controller. And then you're able to get certain notifications and alerts for all of the problems that I've went over. You can either review all of those alerts inside of the platform, or you're able to get notifications. It's very important that if your intersection's in flash, you've lost power, or there's some other major issue at the intersection, there's some way for you to be aware of that so that you can jump on those problems and solve them as quickly as you can. Because when it comes to a dramatic failure at an intersection, that is the highest impact on congestion. So you want to get out there as quickly as you can. Next, I want to go over intersection utilization, which is obviously a key factor for understanding congestion. So a good count platform will be able to tell you not only how many vehicles have gone through the intersection of the day, but it should give you granular detail like we can see in the bottom, where we are seeing exactly how many times each type of vehicle took every movement. This is a really good way to figure out if maybe you need to allow for extra time, extra space for a tight left turn because there's a lot of very large trucks moving through. It gives you an idea of the bus traffic and bicycle traffic so that you can account for those variables. And it really gives you all that you need to know about how the intersection is being used. A lot of companies, including MyoVision, also offer temporary studies where you can track the count data at an intersection just over the course of about 2 weeks. But using a permanent solution is an easier way to make sure that you're tracking consistently the utilization of your intersection. And that's going to come more into play once we talk about before and after closer to the end of the presentation. All right. Reducing collisions, of course, is a great way to minimize the congestion at an intersection. Crashes can be a major source of collisions, so of congestion. So making sure to reduce those collisions before they occur is a really great way to avoid those pitfalls. So by tracking near misses, the number of times that two objects almost collided, and tracking the severity of those near misses so you understand how close that was to being a fatal accident is a great way to take preemptive measures to improve the safety of your intersection before collisions occur. Um, since you're able to collect that on a regular basis, it's a lot more reliable than crash data, which often misses a lot of details and is very spread out. So using a system that allows you to do near misses really gives you a full picture of what's happening at your intersection so that you can make direct interventions to make sure that you're reducing this potential barrier. So next we have conflict clips. This is just a demonstration of how MyoVision's near miss works. You can see it's tracking the two objects that almost collided. It's tracking their relative proximity, and it's tracking the relative speed of the inciting vehicle to give you an idea of how close that was to an accident. I find the one on the right to be very revealing because it shows that one vehicle was completely unable to see that pedestrian until they almost missed them there. So perhaps this is a case where we need a dedicated left if this intersection is so busy, just to make sure that that's a protected movement and we're going to reduce the number of collisions into pedestrians. Right. We're also able to measure the effectiveness of some of the other systems that we went over. In the case of transit and freight effectiveness, it's a little bit more direct. We're able to tell you things like how long the vehicle was stopped along the route, how long it takes between stops, the total travel time, as well as the time that the vehicle has spent stopped at signalized intersections. So this is a really great way from the transit and freight side of the house to understand how congested that route is. And there's lots of different things that you can do. You can either talk to the traffic engineers about working out how to improve the operation of the intersection as a whole, or you can investigate potentially giving more allowance to your TSP green times. Um, we carry on. We're just about done here. Um, next slide. Here we go. The last thing that I wanted to talk about are ATSPMs, using data over time to measure the impact of these systems. So you can use simple data points or data over time to understand not just how your intersection's doing, but how the changes that you're making at your intersection, whether you're implementing freight control or TSP or some other system, you can get a good idea of how those changes have impacted the intersection as a whole. Because we want to make sure that we're reducing congestion and not just reducing congestion for certain individuals. So leveraging ATSPMs to understand the impact of overall traffic is a really important part of that discussion. Right, and I'm just going to skip through the next two slides pretty quickly here because I think I'm eating into some time here. I wanted to talk about the this slide here. This is a really great page for understanding the impact of emissions, right? You want to be able to articulate for folks who aren't in the traffic space what the positive impacts of the actions that you've made are. And a really good way to do that is to put it in terms of cost and emissions. So if you can allocate a certain cost or CO2 waste to delay at an intersection, you're able to sort of score things over time to provide a before and after data on how the changes that you've made at your intersection have made an impact both to the citizens and to the environment. So as you make changes and you're wondering if you're moving in the right direction, it's always good to verify that. And that is all for me for this presentation. If you have any questions or queries, feel free to email me at that address there, and I'll make sure that you're sent over to the right folks at MyoVision. Um, Thank you very much for the time to speak.
Thank you, Brad. So next up, we have Seth Searle with Kimley Horn. Seth is an electrical engineer who has worked at Kimley Horn for 15 years, designing, developing, and integrating a wide array of traffic applications. Seth's core areas of expertise include centralized signal systems, adaptive traffic control, transit signal priority, emergency vehicle preemption, and connected vehicle applications. As a project manager, Seth recently led the successful deployment of citywide central EVP in Surprise, Arizona, and has been one of the key architects behind many TSP, EVP, and FSP related features in Kimley Horn's traction priority software, which I believe Seth is going to discuss in his presentation. Seth, the floor is all yours.
Excellent. Thank you, Alric. I guess no further introduction. I appreciate the intro there. Now, before I dig in, as we kind of chatted about earlier, a lot of us kind of work in similar spaces. I think Brad gave an awesome presentation on some of the stuff they can do. Our focus, or my focus on my portion of the presentation, is going to be a little more on the key performance indicators. So, don't take any of this, whether on Brad, with some of what Brad showed or some of what I showed, that, we do or don't do certain things. I think we're both just trying to showcase different things that are possible in this space. So key performance indicators and some practical applications are really what I'm going to focus on here. All right. Yeah, you can move it right along. So I'll give a brief overview of traction priority. So yeah, before getting into any specifics, I like to just kind of set the stage so you all know what I'm talking about, what our software does. So yeah, Alric, go ahead and go to the next slide. This graphic here is really an all-in-one graphic that represents Kimley-Horn's smart cities technology solutions. We really have a full smart cities ecosystem. KITS is our original solution, originally developed in 1989, deployed in Windsor, Canada in 1989, still running to this day. So 35 years of history built on signal communications, implementing every type of signal firmware protocol under the sun. And really the rest of our solutions and the rest of what we do in the space of traffic has branched off of that original signal system. The next bubble you see there is Cadence. That is our adaptive traffic control module. I'm going to gloss over that. I'm not really going to focus on that much today. But I will just say, as similar to kind of what Brad described, a lot of us in this space make sure that these solutions work together in a cohesive ecosystem so that you can leverage TSP, EVP, adaptive control, and a variety of other signal technologies in a single deployment. So I'll just kind of underscore that that cadence can be woven in on those as well. The last bubble you see there is traction, and that is sort of a catch-all term for what we call our traction smart cities ecosystem. And there are 6 different modules that traction is comprised of, all cloud hosted. They all focus on different areas of traffic control. But the big picture with this graphic, the interplay of these solutions, this ecosystem that we've developed, really help tackle all of the use cases you see around those spokes on that graphic. So whether it's connected vehicle applications, adaptive control, inventory applications, transit signal priority, these solutions work together to really provide all of these use cases. All right. And then this graphic is a little bit of a drill down into that traction ecosystem. I'm going to go through this very quickly. Traction travel on the left-hand side is for travel times, pulling data from crowd sources and mobile app generated data for, analyzing travel times along corridors and using it in our solutions to do smart things like decision support, alerts, lots of other good applications there. Traction Metrics is our ATSPM solution, which is built. It's a heavily modified version of the UDOT open source system and interfaces with that solution. Traction Workflow and Traction Live are, I'm kind of lumping these together. These are more add-ons to KITS, the KITS signal system. These provide some web-based features, more browser-based dashboard views and workflow management capabilities. Traction Connect is our connected vehicle solution. This interfaces with roadside equipment, basic safety message data coming back from vehicles, and has a whole web interface to visualize that data, see the status of devices, create map files to load onto your roadside units, and then also comes with a mobile app for sort of virtualized CV applications. And then finally, where I'm going to spend the rest of this presentation is on Traction Priority, which is Kimley-Horn's transit signal priority and emergency vehicle preemption solution. All right, and yeah, this next graphic here, this just summarizes at a high level how traction priority works. So yeah, if you don't mind going back to that graphic just real quick there, Ulrich. So just to explain, folks on this call are going to be familiar with a lot of these concepts. I'll just lay it down into 2 basic ingredients. A connection to vehicle data. So some connection that provides us speed, location, and heading of the vehicles that we want to provide priority for. And so that'll often be AVL feeds, it can be CAD feeds, and in some cases, direct connections to onboard equipment like cradle point routers, EtherWAN devices. And then also we have our own mobile app that can be used to generate AVL data for any vehicle that may not have any onboard equipment. So that's ingredient one. And ingredient two is the connection to the traffic signal controller. So as long as there is communication, some type of communication to the traffic signal controller, we can use typically NTCP messaging, but there are legacy controllers that we support as well that do old protocols like QuickCom and AB3418. As long as there's communication and a protocol that the controller supports, and they support some type of preempt or TSP remote commands, that's really all that's needed to make the system work. And the graphic kind of speaks to the rest. So yeah, just some brief characteristics. Yeah, sorry if you're struggling there, Alric. I'm not sure if there's like some advanced timers going on these slides. I see that happen sometimes.
Yeah, I believe it is. So yeah.
Yeah. Yeah, if you need to take a minute and take those timers off, but I'll keep going. Let me know if you need me to pause. I've had that happen many times in my presentations. So just some quick characteristics about traction priority. So fully cloud-based. The graphic that you saw before, the quick way to summarize this is fully deployed in the cloud. There's no equipment that goes in the cabinet, no equipment that goes in the field. The only consideration that does need to be made, and this is going to be true of any smart city solution or IoT, Internet of Things solution, you do need typically some type of edge processing. So while we can pull signals straight from the cloud, modern security standards and agency IT departments typically prefer that is done on the agency network. And so I just bring that up sort of as a disclaimer. While this is cloud hosted, the practical considerations usually require us to do that polling, the connection to the signal controllers on the agency network so as to comply with firewall rules. But all other processing is done up there in the cloud. We support all modes of transportation. I think you're going to see that largely of all of us operating in this space. There are many vehicles out there that would warrant priority. There are many different types of priority that controllers support. I think Brad did a great job covering that. Another characteristic, scalability. This is something that's great about cloud-based solutions. It can scale endlessly. We have the capability to just continue to leverage more resources as you get 2,000 vehicles, 5,000, 10,000. And beyond that, this allows the connection of different agencies together. So you'll see in one example, we've implemented freight priority in North Central Texas, and that involves providing priority to up to 10 different agencies in one solution. Something that would historically be very difficult to do across disparate networks, but is made a lot easier through these modern cloud platforms. I'm going to skim over the algorithms, but yeah, there are a lot of innovative algorithms that can be used in the cloud to facilitate transit signal priority, business rules, some of the adaptive control that can be woven in are some good examples there. And then finally, the key performance indicators. Alric, let me go ahead and just pause here real quick. Do you want to turn those timings off? I can show you where they are if you want to quickly turn those off so we're not constantly battling this.
Please do.
Yeah, just hit escape real quick. And if you're in PowerPoint, there should be a timings view. If you go to the slideshow tab, I believe. And the use timings checkbox, uncheck that. There you go. Let's see if we can't make this a little more pleasant for folks.
Yeah.
All right. Yeah. All right. So yeah, this is good. So key performance indicators. I'm going to go through a little bit of what we are doing here. So the reason I wanted to focus on this particular topic is, there's a lot to say about how TSP is done and what it can do. What we have really been delving into lately and what we see a lot of interest in is what kind of benefits are we actually receiving? If I'm going to invest in a solution like this, what would that return on investment look like? So that's really what this section is designed to cover. What we are attempting to do to display those types of savings. So what you see on the right-hand side of your screen is what we call our KPI dashboard. So KPI stands for Key Performance Indicators. This is a separate standalone dashboard that can be made available to any stakeholders, as part of a TSP freight priority project. And what this does is it hooks into the traction priority system, and it uses, if anyone's familiar on the call with EPA moves, this is an official modeling system by the EPA that provides the appropriate calculations to calculate emissioncy savings. So fuel savings, which translates to emissions and cost savings as well. So what's underpinning all of this, the ingredients that go into this, are the cloud-based TSP solution, which is gathering second-by-second traffic signal data. So all of the phasing information, when phases are forcing off, when transit signal priority is being granted, coupling that information with the information from the AVL feed, and using a number of traffic engineering calculations. There are some projections you have to do to really capture benefits. So I'll give one brief example. If you have a bus traveling to an intersection and it was going to arrive on red, but the green was extended and the bus was able to get through the signal, you might traditionally just think, oh, this bus saved maybe 45 seconds of idle time because it got a green light and didn't have to sit at that red. There's a downstream effect, though, where a lot of the times that one TSP grant, that one green extension, can put the bus in what we call the green band and basically set that bus up into that sweet spot of the timing where all of the next 3, 4, 5 signals, it could potentially get a green light without any further TSP activity. So that's just an example of some of the traffic engineering we have to do to really figure out what the bus would have done versus what it actually did, plug it into these EPA moves calculations, and then display those savings through this dashboard view. And you can see some of the other notes there on the right. It works for transit and freight. Little trickier to do for emergency vehicles, but that's definitely something we're looking to repurpose this. And this also integrates with a GLOSA recommendation. So this was a unique part of the North Central Texas project where there's a green light optimized speed advisory app that the freight operators are using, and the benefits of them falling within those recommendations and getting better green time, more green lights as a result, are also being measured here. And then if we advance ones, we'll go pretty quickly. These are some of the drill downs that are available for each of these metrics. So travel, it all goes down to how much time, thus fuel, thus emissions, thus cost, was saved by the system operating effectively. So this is the breakdown of the travel time savings. So what did you save in terms of minutes? Next slide. We have fuel savings. So this is based on all that information, those calculations, how much fuel was saved. And I'll just briefly mention, as you look at these different panes, you can fully drill down. This is broken down into every single TSP action. Those, you see 0.083 fuel savings. You have full visibility, full drill down into all of this on a per vehicle level, per fleet level. With freight priority, there's a number of different fleets operating. So this will also support rolling that up, based on the filtering of the website to see those benefits across the entire fleet. Go ahead and go to the next slide. This is, again, just another view, the translation of fuel savings into cost savings. Now, one note I want to make on this, this is something I think we anticipate getting a little more complex. And I'm going to give one more quick example. We always focus on fuel savings, but something that was kind of illuminated to me when we did emergency vehicle preemption is the wear and tear on brake pads, for instance, for a fire truck that is loaded with a full tank of water is massive. So when we are able to get them a green light and prevent them from stopping, it's not just fuel that's being saved, but there's also the wear and tear on the brake pads and other components. And so the cost savings, while right now this is tied more directly to fuel, It's kind of an unspoken benefit that I haven't heard mentioned a lot, but does seem to resonate with those that actually maintain these fleets. Like, hey, there's more than just fuel that we can benefit from. So that's something else that we'll be aiming to capture. Go ahead and go to the next slide. And this is, again, just another visualization. This gets into the emission reduction. So of those, the fuel savings, the cost savings, what did that amount to in terms of emissions reduction? All right. And then I think we have one more here. So this is sort of a separate display. This is hot off the presses. We are just wrapping up development on this display now, but I wanted in the vein of key performance indicators and more specific to transit, where there's a concept of a fixed route, predictable trips that are happening. We've also developed a dedicated route status display that allows, as the TSP system is running, allow to go back and view every single bus trip, where different actions occurred, where the slowdowns occurred, whether there was a green success versus an arrival on green, which there is a distinction between the two. You can hit a green light not due to TSP, or you can get a green light due to TSP. So it provides that sort of granular breakdown. And then a number of title cards on the right that show the key performance indicators, or maybe we call these transit signal performance measures. I think that's what I've been hearing these referred to more frequently. Those are calculated on the right-hand side based on the different selections for the display. So this is just another example of some of the stuff that us, and I'm sure many others in our space, are trying to do to take this awesome technology and just show you, like, here's everything it's doing, here are the benefits it's providing, because those are the big questions I think we all need answered. And yeah, just a quick zoom in so you can see in a little more detail there. Yeah, that's good. Just wanted to flash that real quick so you could see the zoom in. All right, and I'm going to wrap up with these last couple of slides here. Just wanted to provide a couple of project examples. So this is the intent with this section is what's happening out in the real world, like what is actually possible beyond the standard stuff we all come to know and expect about TSP. So just a couple of kind of case studies here. Austin, Texas, this is one I wanted to focus on. In this deployment, we actually implemented traction priority citywide to provide both transit signal priority and emergency vehicle preemption in one solution. I want to give a shout out to Brad. I think he did a good job kind of explaining earlier a lot of the behind the scenes, like how this is possible and how this equipment, a lot of it can be used to do the same thing. And he's spot on. That's exactly what we're doing here in Austin, Texas, obviously with that more cloud-based approach. I think another notable piece here is this was an early litmus test for our solution specifically on just how well those scalability claims hold up. I mean, I think we all believe and we know that you can scale endlessly in the cloud, but there are sometimes other factors that make that not so straightforward. So this was a great litmus test and did validate and prove that this system can work just as well with 2,000 vehicles as it can with 50. So just wanted to note those 2 points there. Move on to the next. Los Angeles, California, we're implementing a transit signal priority for LA Metro on over 1,600 signals. What I wanted to highlight about this is the ability to still do TSP with a non-traditional type of deployment and a non-traditional type of controller. So in California, they have their own firmware. There's an LA DOT firmware that runs in the LA area. There's LACO 4E that also runs in Los Angeles. There's Caltrans TSCP. None of these firmwares support NTCIP. They support old versions of AB 3418 and in some cases their own custom protocols. So this was an especially unique one because there was no polling to the signal controller. The status is coming back to us through a SPAT feed. So all of the actions from the controller, we actually receive secondhand from a SPAT feed that's running twice per second. So we are getting the data very quickly, in some cases even faster than when we pull controllers directly. And there is a secondary COM port in these controllers exclusively for handling TSP requests. And we are, instead of communicating to the controller, we're communicating to a what's called a TSP emulator that LADOT staff has written and provided to us. So I bring all of this up just to say, even if you have non-traditional controllers and a setup that isn't as conducive, there are a lot of things you can do around the seams to still make a cloud-based solution work. And then just another factor here, there's a lot of closely spaced signals. There's a lot of talk about, well, what's the best strategy to take when you have very closely spaced signals in a downtown area. And we've implemented some really clever time to arrival algorithms that go down multiple signals to get those TSP requests propagated ahead of time. And I think I have just two more quick slides. Indigo, this is the Indianapolis transit group. And in this project, we implemented more selectively traction priority on 2 of their BRT lines. I wanted to note this one of the unique aspects to this project was the integration of real-time feedback via the Traction Connect mobile app. So if you recall the slide that we had up very briefly earlier, Traction Connect is our connected vehicle solution. We are using the mobile app that can basically be used as a mobile BSM and shows that type of GLOSA display. So it shows the real-time signal status to a user through the mobile app as they approach the signal. The same kind of philosophy as map and spat data. That app has actually been hooked into our TSP deployment and is relaying to bus drivers whether or not they received a TSP grant in real time. So this was a kind of a first of its kind. It's instead of looking back after the fact, let's actually show this as it's happening to the person driving the vehicle, what the signal is. So I thought that was a really cool thing that we were able to implement in this project. And then this was a good example of some of what you can do with certain controllers. The Econolyte controller, the EOS or EOS specifically, has varying levels of priority that can be assigned to any vehicle type. So you can effectively give something like preemption to a bus, or you can dial it much further down. So there was some unique aggressive priority that the stakeholders wanted to implement here that we're doing that's a little more aggressive than we've seen elsewhere. And I wanted to highlight that that was kind of a unique Econolyte feature and a good example of what you can do with certain firmware that you may not be able to do with others. And then last slide here, and I will be done. Surprise, Arizona. This was one Alric mentioned in the intro. We just finished deploying the central emergency vehicle preemption part of traction priority citywide. 71 traffic signals now. They built a few signals in the last year. They have 35 city fire trucks. Not a note on here, but they also have fire trucks from neighboring jurisdictions that we're accounting for. In this particular case, we opted and the city opted to install new equipment. And we went with the EtherWAN routers because they were able to provide us vehicle speed, location, and heading once every 0.9 seconds. And they were able to take the optical emitter. So this is kind of a nice way that all of our worlds tie together. They're able to take the existing optical emitters on their fire trucks that have been on there for ages and have worked with the legacy optical systems and tie that input into the router so we can use that as a flag to selectively provide preemption only when not just when the lights and sirens are on, but only when the optical emitter is on, which gives us like really good control over when we should and shouldn't provide preemption. And of course, that implies the legacy optical system is remaining in place. The city wanted to keep that as a redundant option. So this was a great example of being able to use 2 different technologies at once. The optical system is still running great. The cloud-based system is operating on top. And if one system has some kind of edge case where it doesn't capture, the other is likely to pick it up. The last 2 things I'll mention, we implemented a unique algorithm that we call Get Ready Mode that allows us to start PED clearances early and get the preempt to take faster. They do not truncate their PEDs in surprise, so that's a concern there. And then I mentioned briefly, I talked a little bit about mobile apps. We have a dedicated mobile app that can be used for testing at any point. It has a dispatch simulation feature, and this allows for testing of the solution from any vehicle without having to install any equipment. And that's it. That's everything for me.
A little too quick on the draw. Appreciate your presentation, Seth.
Thank you.
So, next up, we have Peter Kuntz with the City of um, Portland. Peter's been a transportation engineer for the last 30 years, serving as manager for the City of Portland Bureau of Transportation Signals, Street Lighting, and its ITS division. He's also worked in the private sector, private practice, um, with transportation projects across the US and Canada, including significant research projects for the National Cooperative Highway Research Program. Peter served as an adjunct professor at Portland State University, teaching graduate level courses in transportation engineering, and he is also very active on the Transportation Research Board, having served as the chair of the Committee on the Traffic Signal Systems. Peter, handing off to you. The floor is all yours.
Great, thanks, Charlotte. Yeah, happy to be here today. Want to talk about signal priority. I'm going to actually, give you a little quick history on Portland, but actually, I've been serving as a consultant to the City of Ithaca's SMART grant, City of Ithaca, New York, and they're doing signal priority, so in a creative way. So with that, jump on in. Which is a quick disclaimer. So these are based on my videos and opinions. So I just wanted to let you know that some of this is incorporating some information from companies that I've dealt with in my history as a traffic engineer. Next slide. So trying to kind of think about the history here in 2000, gosh, I feel like I'm dating myself now. We implemented signal priority. We did it in conjunction with transit and emergency. I'll talk about the technology in a second. But this again, before the cloud, before some of this new things that you've seen from the previous two presenters, we introduced freight signal priority measured based on the length of vehicle at an intersection, and said, yeah, we can make some modifications to that. We've done some expansion. We're thinking ahead to connected vehicles, bicycles. Really interesting to see Brad and Seth talk about this. I'll just give you the perspective from an agency that you may be dealing with, maybe a small agency. So let's flip to the next slide. This notion of, when we think about this, I guess I'll just maybe give you if I'm looking at Seth's presentation, the idea of trying to implement and go backwards in technology, to me, is a little bit of a rough sell. I think that the idea, and I'll give you some rough costs on this, most of our traffic engineers should be working towards connecting to the internet. I think that's kind of part of the smart city. Connecting through to the cloud is get a bit of a stretch for some of our agencies. So just kind of know that. These are the presentation you've seen are kind of the next level sort of ideas. And most of our agencies are not quite there yet. So I'll just put that as a word of caution that your technology and your local agency may vary. Next slide. So I said Ithaca, New York, small agency, 30,000 people, but went in on a smart grant and said, gosh, can we do signal priority? So I'll just talk about the who, what, when, and why. Next slide. The who and the what is really, we looked at the small city, and actually it was both city and state Department of Transportation there. We said, gosh, you have to start with communication and traffic signals, communication and controller upgrades. But then, who would we provide priority for? And so from a fleet operator standpoint, it's kind of a who is ready from a technology standpoint. Next slide. So we did a scan of, who are the fleet providers. And so fire, if you're a city, the city is operating their fire folks. But they went in on the school district, which is something that, again, this is a new partner for us, is thinking about school buses. And I love this sort of outside the box thinking. Next slide. So public transit could be one, fire trucks, freight providers. I could think about Amazon. I've worked with Google gosh, should we be thinking about Google buses and Google cars in the future? You get really the opportunities are endless. But you got to do a lay of the land and assess your technology. And are you ready for cloud-based, or is there something more rudimentary that would, from 20 years ago that we would want to do? Next slide. I would say I borrow this slide from Kimley Horn because I love it because it does incorporate all the various partners here: rail, buses, freight, autonomous vehicles in the future, pedestrians, you name it. I think we can think about where do we go with the technology that's at our fingertips. Next slide. But it's not just at our fingertips. We really have to dig into where are we at related to the technology on the vehicle side, and there's a lot of different AVL vendors out there. Next slide. Sometimes we have to upgrade those. Sometimes we can think cellular. Can we use those technologies? Are they ready? Can we tap into those various devices? Next slide. Or do we have to think more broadly? And are the people ready for it? So the various agencies, who would do this work? And in this case, the city of Ithaca selected a contractor that led the project. We're still working on the contracting things, but all these various folks had different questions. And so New York State DOT had different investments they were wanting to make. Ithaca IT had cybersecurity questions. So a whole host of things that were really key challenges we went through that I could, of course, go on and on about all those details. Next slide. I mean, in the interest of time, I'll just boil it down to, if you're going into a cloud-based realm from a fleet vehicle perspective and going to ask the traffic signal agency to accept a message from outside of their normal operations, there are going to be cybersecurity concerns. And in fact, actually in Ithaca, they selected this contractor that included BioVision as the technology. And the fascinating thing was the state DOT had already been using that technology. But the state DOT also started to ask, well, wait a minute, where is the cloud data going to? Is the cloud data secure? Is it a private cloud? And so I'll just say that those sorts of aspects can really bog the conversation down if you don't address them at the onset. The last bullet slide, I'll just say, is also a huge issue for us as we think about the software costs. And so this notion of how do we get from capital investment to ongoing software costs is a big deal for local agencies that aren't used to dealing in that realm of software as a service. So there's a lot of different ways in which we can go about dealing with a message from a bus to the traffic signal. I'll just say again, they're still in their infancy. This realm of smart city is still, I think, gosh, we've been talking about this for a long time, but the state of technology at our traffic controller still pretty limited. So there's a lot of questions. You're going to hear from King County Metro next. They are also on the cutting edge of this, and super excited to hear Owen present his perspective next. Next slide. So if I think about this from a fleet provider's standpoint, what I would do, go to the next slide, is really take on this idea of the first thing from a traffic agency standpoint is we need communication to our traffic signal. And I'm here to say in Portland, about 65% of our signals have communication. That leaves a lot that are not going to be ready for any sort of cloud-based or next generation transit signal priority as we talk about it. It also means that we don't get data back from the field. So this idea of automated traffic signal performance measures that you saw both folks talk about, gosh, that's something that we would love to have that capability ubiquitously. Some agencies do. The Smart Grant is going to provide that through a cellular connection for Ithaca. And so that's, again, one of those aspects that I'll just say, that is a requirement as we think about getting this data back. And then the other part of that is, gosh, if you do provide this new technology from a fleet vehicle, can we jump ahead to signal priority? Can we actually use that and use that to move people? I would tend to argue the point that actually, if I'm a transit provider, moving people is more important than moving cars. And so actually congestion can be a positive influence on encouraging folks to take transit. So maybe a little bit of different perspective and policy than what you've heard earlier from Brad and maybe a little bit from Seth as well. So next slide. So this idea of technology requirements, yeah, I would say if you're starting from that conversation, if you're working with an agency, start with the idea that gosh, you're going to have to upgrade the traffic signal, whatever vendor you're going to provide. Transit priority could come from localized technology, could be a central system like you saw Seth talk about. Both those options are very good. And the idea of how we pull us together so that we're not just building a one-off, that it's really a building block to a better traffic signal system in the future to meet all of our needs is really key. In the case of Ithaca, just small agency, you really needed somebody to bring it all together to integrate it. And so we were super happy in that case to have an integrator, a contractor do the work. In a bigger city like Portland, you really have to, work within the constraints of the existing system. Next slide. Detection, in our case, in the Ithaca example, super excited to have MyoVision be a part of that, because you're adding the wonderful thing of having signal detection. I will say, there are some challenges with the video. Detecting cars is one thing, detecting bikes and pedestrians in the nighttime conditions especially is a little more difficult. So keep that in mind as you think about the various pieces, that those aspects are very important for the traffic engineers, if you're introducing new technology, to kind of consider. Next slide. So conclusions, gosh, if we're talking about signal priority, a lot of attention to details. I could go in, I think you'll hear a little bit from Owen about, the more about transit priority. If you think about freight, if you think about, the notion of school buses, there are really substantial benefits. I loved Seth's comment on brake wear and tear. As a city, I like to think about the wear and tear on pavement conditions. And, you think about heavy vehicles hitting the stop bar, or heavy vehicles starting from on an uphill approach. These are things that I think we haven't completely quantified. And I'll just say, I think we're leaving a lot of money on the table, not only fuel cost savings, but also benefits for our community. Requires significant coordination. You'll hear that from Owen as well. And then this notion of how we pay for it and how we have continuous feedback from our signal systems, that's the thing that keeps me excited about the future as we contemplate additional technology on our streets. And with that, I think that was my last slide. So I'll leave questions for the end. Thanks so much for the time.
Okay. Thank you, Peter. And so yeah, next up we have Owen Kehoe. Owen is the lead transportation engineer in the speed and reliability group at King County Metro Transit in Seattle, Washington. Owen has over 20 years experience at Metro implementing transit preferential treatments to improve bus operations on arterial streets, including transit signal priority. Owen has been responsible for hundreds of transit improvement projects throughout King County and working in collaboration with many of King County's 39 local cities, as well as WSOT, WSDOT, I'm sorry, and King County's road services. Hey, Owen.
Thanks, Alec. Yeah, glad to be here today. So King County Metro has been doing TSP for well over a decade. So I thought today I'd just kind of share what our experience has been doing TSP and where we're headed in the future. So next slide. So quick overview, what I'll go over today, just kind of, first of all, what is TSP at a basic level, why we've done it and what benefits we've measured, where we currently have TSP, and then how TSP functions, both our current legacy system and then the next gen system that we're planning, and kind of where our future plans are in TSP. So I think just do it really quickly, the other presenters have covered this, what TSP is. So I'll skip over this, but I do want to just cover one terminology thing. You might hear sometimes about active versus passive TSP. And so passive TSP is kind of this concept of where you just adjust the signal timing, assuming there's buses there and you don't do anything special when the bus is there. But what we're talking about is active TSP, is if you detect a bus and then the signal controller does something different. So we originally, our legacy TSP system was deployed as part of our Rapid Ride BRT program, the Rapid Ride A through F line, kind of starting in 2010. And when we deployed that, we did a lot of before and after studies of these lines. And this is kind of what we found is if you're looking just at the traffic signal delay, you can reduce that up to 14%, is what we measured on the E-line corridor. If you're looking at end-to-end travel times, we're kind of seeing savings kind of around the 5% level. It's not huge, but it's a nice little bump in travel time. More recently, on a Rapid Ride C and D line, we did a re-optimization project where we focused on improving reliability. And in that case, we saw an improvement in buses meeting our headway target after doing that work. Next slide. So this is where we currently have TSP. It's a little over 200 intersections. Like I mentioned, our Rapid Ride A through F corridor. We do have a few other high ridership corridors with TSP. So this system is dependent on hardware that's implemented at the intersection. So it's very infrastructure heavy. And this system requires our own fiber optic network that connects all the intersections along these corridors that we own and maintain. Next slide. So here you can see some of the roadside equipment that's part of the current system. I won't go over these in detail, but you'll see over there on the right, this is a special cabinet that's done for TSP. So you'll see the lower section, that's where the city houses their signal traffic control equipment. And then on the upper section, what we call the freezer, that's where Metro has access and we have our equipment stored. This stuff is all very expensive to install and maintain. So we want to move away from doing the roadside infrastructure type TSP. Next slide. So what we're moving into is what we call our next gen TSP system. So the older system, besides being hard to maintain, it's also been we've had intersections go offline, like a car hits the cabinet and then the communications down for the whole corridor. So we want to improve the accuracy and reliability. But our main goal is we want to reduce the cost of deploying and maintaining the TSP system. And also we want to, the cities have already built all these communication systems to the traffic signals. So we want to be able to leverage that. And our buses have cellular communication. And so we want to be able to leverage these new communication systems. So we're moving to kind of a cloud-based system. Next slide. This is the architecture that we've developed under Next Gen TSP. So we currently have a fleet of about 1,500 coaches. So we did not want to have to add any hardware onto those coaches because that would be a big expense. But we already have our CAD AVL system run by a company called Init. So we had Init modify their software to create a dedicated feed just for TSP. And so every bus in service will ping its location once a second, and it sends it to this TSP data server that's managed in-house by King County Metro. So it takes all the data from all the buses in service, and it kind of repackages that data to send to various cloud services. So we call it TSP request servers in this slide. So Metro is contracted with a company called Light, LIT. And this can provide TSP anywhere throughout the county. So any city that we want to do TSP with, they can connect to the Light system to provide TSP functionality. In the city of Seattle, there's a company called Unix. They have a NextConnect server. So this is an independent cloud-based server that they've been experimenting with. But we've also been trying to get Light to work with the city of Seattle intersections. So we have a lot of different options for what companies we use for TSP. in the city of Bellevue, they use a company called Nicander. They kind of wanted to build their own system. So we have feeds set up for all these different vendors. So we could, if a city wanted to partner with MyoVision or the traction control, we could create a kind of data pipe to get them set up pretty quickly. This also is that location feed. It's once per second. This is a higher resolution data feed that's available in our GTFS feed, and so we've kind of been thinking about are there any other uses there are, like maybe for fleet management for that feed. Okay, so everything we talked about is how to track the buses and detect when they're approaching traffic signals. But now, what do you do once you've detected a bus? And so this is what happens at the traffic signal controller, is the software running there. So we have what we kind of consider legacy TSP strategies. So these are kind of the older way of doing TSP. So you could do green extensions. So if the bus arrives on green, you're extending the green for a few more seconds. Or you have early greens, where if the bus arrives on red, you shorten the other greens and give the bus kind of a little bit of a head start. In a few limited locations, we've been able to do what we call full priority, where you skip the other phases and provide immediate service to the bus. And generally, there's these restrictions. We can't shorten any yellow or flashing don't walk times. If there's any emergency vehicle calls present, those obviously get priority. And then after you do a TSP routine, then there has to be some sort of recovery. Like you have to make up that time in the cycle somehow. And these are covered under an older NTCIP standard called 1202. So the older traffic signal controllers can receive the 1202 message and activate these kinds of strategies. Next slide. So the newer types of strategies, kind of what we consider kind of the next gen type of strategies, is covered by this NTCIP 1211 standard. And the big difference here is rather than requesting priority now, so here's the bus, do something. The 1211 standard allows for an ETA message. So basically, as the bus is coming, even up to like 2 minutes in advance, you can start sending these messages, and the traffic signal controller can start doing more subtle adjustments to anticipate the bus arrival, and then ideally, have the signal be green as the bus arrives at that ETA time. And if done right, this can have a lot less impact to other intersection users. You maybe don't need to do phase skipping or shorten the phases quite a bit if you have this ETA information well in advance. This can also handle near side stops. So if you have a bus stop before the intersection, the system can learn over time how much time the bus typically takes to the bus stop, and use that to help choose an intelligent ETA. This is something where transit maybe has a leg up on emergency vehicles, because we have buses doing the same route hundreds of trips a day, and so we build this pretty rich historical data of how long the bus takes to reach a particular intersection. Next slide. And besides those strategies, kind of some stuff we've been thinking about in the future. We're looking at potentially integrating TSP with active service management. So ASM, that's basically where rather than the buses running to a schedule, you have a dispatcher actively trying to keep the headways at a constant spacing. And we could potentially use TSP to assist that. So if the buses start to have a big gap in service, you could start giving extra priority to that bus to help it catch up. We've looked at doing some enhanced pedestrian signal timings. So as the bus approaches an intersection, there's people that want to cross the intersection and get on that bus. So you could potentially activate a ped phase before that happens. I think City of Portland actually does this on the Division Street BRT corridor. And then after the bus drops off people, they're going to want to cross the street. So you could activate another pedestrian phase there. And we're looking at using the TSP system as a better detection for special bus only signals and queue jumps. Currently, we just use like standard loops for video detection, but with TSP, you could maybe provide more advanced detection. Next slide. So this is my last slide. This is kind of our current master plan in terms of TSP. So this shows all the lines that we currently have planned for TSP at some point in the future. And this is a combination of replacing existing TSP with lines that have it now and new TSP corridors. And I haven't tallied up all these intersections yet, but I think we're kind of approaching 1,000 intersections throughout King County, once this full plan is realized. So next slide. I think it's the last one. Yeah. All right. I guess we'll open it up for questions now at this point.
Okay, I want to thank each of the presenters again. One last slide I want to share before I stop sharing my screen is if you want to stay involved or learn more about what the Clean Transportation team does, we encourage you to sign up for the newsletter by scanning the QR code. And again, we want to thank Geotab, eBoost, Leak Services, as well as United Soybean Board for sponsoring our events. Like I said, we're a public state agency that basically is quasi-governmental that relies heavily on grant funds. So none of the initiatives that we do could be possible if it were not for sponsors such as these. Now I'm going to go ahead and open up the floor to question and answers. Start with anybody from the audience. Do we have any one that has anybody that has any questions? Okay, if not, then I have a ton of questions that I can definitely fire off with. Um, Start off with this. So, if multiple calls are being placed at the same time, which of those calls is addressed by the controller? And any one of you all feel free to chime in with your responses.
Sure, it's generally going to be dependent a little bit on the configuration, but the way that's usually done is through a balance of conditional priority within the wider brackets of high priority and low priority. So you can set the relative priority of vehicles so that if they arrive within the same small window, it will give the priority call to whoever has the higher priority in those groups. However, if you have one vehicle that's showing up well before another, you may run into the possibility where a preemption call is made for the lower priority vehicle before that higher priority vehicle arrives. In the case of EVP, that would override the transit signal priority call, but there are some cases where a lower priority TSP call will be handled over a higher priority TSP call based on which one arrives first at the intersection.
Yeah, and I can just add to that. I mean, I think the term to cover that is really business rules. I think, all of us providing these types of solutions will have our own different spin on business rules. So like just to kind of give an example, sort of how we do it, as we're pulling in the vehicle location updates, all the information from the feeds, we're getting real-time information on headway, schedule adherence, occupancy of the bus. And that really gives us a lot of data points to key off of. And we can set up sort of complex logic to say, yeah, if you have a bus that's on schedule and that does not need priority, and then you have a intersecting route that has 5 buses all somewhat closely spaced next to each other, the business rules are really what allow you to really granularly define that however you want to.
And I'll just add our legacy system is currently just first in, first out, or first come, first serve, which is that's just a technical limitation. With our new next gen system, I mentioned that we're looking at integrating it with active service management. And we're thinking particularly our most recent rapid ride line we launched was the G line, and it operates on 6-minute headways. And so, both directions that at each intersection, that's a call every 3 minutes, and that's like too much to do TSP for every one of those. So that's a way we can use the active service management to kind of target those calls for the buses that really need it. So that's kind of one of our reasons for doing that.
Yeah, the newer the model of TSP that you're using, the more customizable it's going to be, as Seth mentioned. So we move for, obviously first we started with completely first in, first out, and then in the newer technologies, it gives you more and more parameters to sort of configure the conditions that go towards that.
Yeah, just real briefly, Owen, you touched on something that I think is actually coming front and center in the last year or two. Practically speaking, when we implement TSP, I think most agencies are taking an approach where we want to vet this out. We want to know it's working. So it's kind of open the floodgates. Let's provide it everywhere. So yeah, that's what we're seeing in a lot of our deployments. I think we're in a mode where folks want to see the system working. What I've been hearing more and more from transit operators, from folks that maybe came from some of these companies in the past that I had a chance to connect with, is you can actually do more harm than good doing that. Providing TSP to a bus that does not need it and getting it ahead of schedule can be a very bad thing, or maybe not a very bad thing, but it can cause actually a problem that would not have existed if you hadn't provided TSP. So we're kind of in an interesting space. We're probably still going to see these widespread deployments, but I think we're going to see the throttle kind of dialed back a little bit as this gets vetted out. And really that more selective priority, I think, is going to be key.
Okay, so we're running a little close on time, and so for that reason, I think I'll just leave it to, I guess, one last question. We could certainly go on with this discussion, but guess just want to see what steps are being taken to mitigate impacts to side street delay when providing TSP and truncating the greens.
Um, I think Owen did a very good job of covering that on his slide. I think the time to arrival based TSP is the biggest one there. I mean, just to dig in on that a little bit, what that really, you can set, like Owen said, you can send very long time to arrivals. I think what you would typically want to do is something lower than the cycle time. So if you have a 2 minute cycle, you can get this command out up to 2 minutes ahead of time. That allows the signal to start subtracting time from phases in that, let's say 2 minute span. Then by the time the bus has arrived, it can serve the phase, and that recovery time just goes way down. So I just want to give Owen a shout out. I think he hit the nail on the head with the time to arrival. And then, Brad, I'll let you speak on this if you want, but the adaptive, I think, is the other big one. If you can run the adaptive system alongside your TSP system, that can further balance those negative impacts on the side streets.
Yeah, and I think a lot of the value too comes from understanding what those impacts are, right? If you've got performance measures showing you your split failures by approach and you implement TSP for the major corridor, it's really easy to track if the split failures or vehicle delay goes up for those side streets. That's where you can kind of understand the consequences of the transit signal priority or freight priority system. So you can kind of dial back how many calls are being placed if you find that it's getting a little bit out of hand.
I'll be a contrarian here. I think it's got to be a function of your policies. In Portland, we want to move the bus. I don't actually care about the side streets so much if I'm moving the bus. So that may not be what your local agency wants to do. So I think it's, again, look at the policies. If it's more focused on environmental goals, people movement goals, then that's the winning strategy as opposed to just worrying about a signal failure on the side street.
And I'll just add I think our biggest challenge in that area has been around pedestrian timings. And a lot of the problems have been around the way that the signal controllers implement the pedestrian timings around TSP. Like, for example, if say the flashing don't walk starts, then here comes a bus that wants the green extension. Well, then the don't walk signal is going to hold a don't walk while the signal's green, waiting for the bus. And then the pedestrians start like, well, I'm just going to go anyway, doing that kind of thing. So we've had a lot of issues with that. We've been trying to get the signal controller manufacturers to kind of address some of those issues, but that's been a big challenge.
I think I might have misspoke a little bit. I mean, if you all want to hang out for a little bit longer, can definitely ask a few more questions, or we good on time? Yeah. Anyone have any other engagements or?
I've got to run. Sorry.
Okay,
Yes.
so yeah, we'll go ahead and cut it short then. Want to thank you all for being presenters for this, and feel free to reach back out to any of these presenters if you have any further questions.
Great.
Thanks.
Thank you, Alric. Thanks, everyone.
Thank you, everyone.
Thanks.